All right, everybody, welcome to another video. So in this video, we'll be looking at complex functions, okay? So usually with a function has an input set, right? And it has an output set, right? Going back to college algebra, right? So a function is you have a number and we want to input it into some machine, right? Some function machine called f, and what spits out is a y value, which is f of x, right? And so these sets, capital X and capital Y, these will be sets, and they were sets in the real numbers, right? And we figured out the domain and range of functions in the real numbers. It's going to be the exact same process with complex functions, but this time we'll be taking a domain X, which is a subset of the complex plane. So we'll have a set in the complex plane, right? Z, and we're going to figure out what output it would be, f of z, in terms of another set in the complex plane, right? Let's say W. Let me do, okay. So the notion of functions will be the exact same terminology, but we'll be dealing with four variables in this case, two real parts and two imaginary parts for the domain and ranges of the complex function respectively. Okay, so a complex function is a function whose input and output sets are part of the complex numbers, right? So this is a function whose domain and range are subsets of the complex numbers. The complex numbers. So here's an example of a complex function, right? It's denoted as f of z, z squared times z conjugate minus 2i, right? And I want to figure out what f of 2i equals to and what f of 1 plus I equals to. So take a couple minutes to write out what those output numbers would equal to, okay? Okay, so I assume that you worked out these examples, so let's actually compute them really quick. So f of 2i is used to replace 2i in the z's in your function, right? So it would be 2i squared times 2i conjugate minus 2i, right? And so this equals to 4i squared, which is minus 4, times minus 2i, that's its conjugate, minus 2i, right? And so this equals to 8i minus 2i, which is 6i. Okay, minus 6i. I. F of 1 plus I, same idea, right? So this is 1 plus I squared times 1 plus I conjugate, so 1 minus I, minus 2I, right? And so this equals to 1 plus, we'll have 2I and then a minus 1, right? times 1 minus I minus 2I. The ones will cancel right here. And you'll have 2I times 1 minus I minus 2I, right? And so this equals to 2I minus 2I squared, so that's plus 2 minus 2I. The 2 i's will cancel, and this equals to 2. All right. So we will assume the domain to be the set of complex numbers, of all complex numbers. Set of all complex numbers. Since the functions are not explicitly defined. Okay. So for the most part, we're going to be assuming the domain to be the set of all complex numbers, right? Since our functions they're mapping a point in 2 space into another point in 2 space. So you'll have functions that are not explicitly defined. Okay. Also, real functions. Okay. So real functions. And what I mean by this is single and multi-valued real functions. So the functions you may have seen in calculus 1, 2, and 3, right? So real functions, I will say that to mean all single multi-valued real functions, right? So these are subsets. This is a subset of the complex functions. Right? Since the real numbers is essentially a subset of the complex numbers, right? The real numbers is just that real number plus 0i, right? Z equals to its conjugate. So in order to figure out how to define a complex function exactly, right? The main idea is we have 2 subsets of complex numbers, right? I'll say S and then S prime for this example. And if I pick out a point in S, let's say Z equals X plus IY, we want to figure out the output values if we map them to the complex function F. Okay, and what they will end up with is some generic point in, let's say, S prime. This is S prime. This is S right here. So I'm calling my output set S prime, and that would be a complex number, let's say W. U plus IV. Okay. So it'll be another point in the complex plane. Okay. So to illustrate this more specifically, let's look at this example. So let's suppose we have a function W equals f of z equals z squared. Okay. Okay. So if z equals to x plus iy, okay, then f of z is equal to x plus iy squared. Okay. And this equals to x squared plus 2yxi plus 2yxi, yeah. And then minus y squared. Minus y squared. So f of z, in terms of the real and imaginary components, are x squared minus y squared, that's the real component, plus 2yx times I, right? That's the imaginary component. So if w equals to another complex number, u plus iv in S prime, then u plus iv is equal to x squared minus y squared plus 2yx times I, okay? So in terms of the real components, u is equal to x squared minus y squared, and the imaginary components, v is equal to 2 times y times x. So this is how you split up a complex number and complex function, excuse me, in terms of the real and imaginary components. Okay, so in general, f of z is equal to u of xy plus I times v times xy, right? So u of xy, this will correspond a function in the real component. V of xy corresponds to a function in the imaginary component. Okay. All right. So here's another example for you to work with. Here's another example. So find the real and the imaginary components of f of z equals to minus 3z plus 2z conjugate minus I. Okay. I'll give you a few minutes to work on this. All right, so I assumed you work out this example here. So if I let z equals to x plus iy, right? Then f of x plus iy is equal to minus 3 times x plus iy plus 2 times z conjugate x minus iy minus I. Okay? And so this equals to minus 3x minus 3yi plus 2x minus 2yi minus I. Okay. So the real component will be the quantities that don't have an I in it. So we would have a minus x as our real component. The imaginary component would be these values here, right? So minus 5y minus 1 times I. Oops. Maybe I'll write it like this, plus I times minus 5x minus 1. Okay. So the real component is minus x, and then v, imaginary component is minus 5x minus 1. Minus 1. Okay, minus 1. So there's many types of functions that we are going to go over in terms of the conformal mappings. There's the natural log function, exponential function. Let's first talk about the complex exponential function. Not the polar form, that's different. The complex exponential form, function, excuse me. Let me rewrite this as function. So e to the z, well, if I let z equal to x plus iy, well, it's equal to e to the x plus iy. And if I do exponent properties, it will be e to the x times e to the iy. But in terms of cosine and sine with this quantity, this equals to e to the x times cosine y, excuse me, cosine of y plus I times sine y. Okay? That's how you define the complex exponential function. Okay, so for example, right, if I were to compute e raised to the 2 plus pi I, okay, e raised to the 2 plus pi I, well, this equals to e squared times cosine of pi plus I times sine pi, right? Cosine of pi is -1 and sine of pi is 0. So we'll have e to the minus 2, okay? And we went over the polar coordinates. Actually, let me rewrite this. So we actually went over the exponential form of a complex number. The exponential form of a complex number. So it's equal to z is equal to r times e to the I theta, right? R is equal to, so if z is equal to x plus iy, right? R is equal to the square root of x squared plus y squared. Theta is the principal argument, right? The argument of z, right? Oh, oops. One of them is less than, the other one's less than or equal to. So this here, that's the principal argument of z, okay? And we also know that since theta can be periodic, right? So, or I should say sine and cosine of theta is periodic. We can also say that the complex exponential is periodic, right? Okay. So we can also express a function in terms of its polar coordinates. In terms of its polar coordinates. So if I have z equals to x plus iy, and we know that x is equal to r times cosine theta, and y is equal to r times sine theta in terms of polar coordinates, we can express f of z equals to the real component in terms of the polar coordinates plus the imaginary component in terms of its polar coordinates, right? So let's see, one last example. So we want to find u and v as functions of r and theta, okay? And the function I want you to look at is this one. Z plus 1 over z. So I want you to work on that for a few minutes and try and see what you come up with. Okay, so I assume you worked out this example. We're going to use the complex exponential for this. So z is equal to r times e to the I theta, right? So we can combine this function into one simple rational function in z. So that would constitute adding and multiplying and dividing by z to get a common denominator, right? So you'll have z squared plus 1 divided by z. Okay. And so in terms of its polar coordinates, this equals to r squared e to the I 2 theta plus 1 divided by r times e to the I theta. Okay. So if I write out in terms of the cosine sine counterparts, so this will be cosine 2 theta plus I times sine 2 theta plus 1 divided by r cosine theta plus I times r sine theta. Okay. And so this equals to r squared cosine 2 theta plus 1. That's the real component in the numerator. Plus I times r squared sine 2 theta divided by r cosine theta plus I times r sine theta. Okay. So now we're dividing complex numbers now. So that means we're going to have to multiply and divide by the complex conjugate on the denominator. So r cosine theta minus I times r sine theta times r cosine theta minus I sine times r sine theta, right? And so the denominator, you're just going to get, you'll get r squared cosine squared theta minus I squared. Okay, so plus r squared sine squared theta. Oh, perfect. Okay, perfect. That's what I need. Okay, so now we're gonna have to multiply this number by r cosine theta minus I times r sine theta. So it's r squared cosine 2 theta plus 1 times r cosine theta minus I times r sine theta plus I times r squared sine 2 theta times r cosine theta minus I times r sine theta. Okay. On the bottom, it's we'll have just r squared. That's a good thing. So we'll have r squared cosine squared plus sine squared if theta is 1. So so we will have r cubed cosine 2 theta cosine theta minus I times r cubed cosine 2 theta sine theta. That's the inside terms plus r cosine theta and minus I r sine theta. Okay. Now we'll have plus I times r cubed sine 2 theta cosine theta minus I r cubed sine 2 theta times sine of theta over r squared. Okay, so from here, this would equal to r cubed cosine 2 theta cosine theta plus r cosine theta I'm just checking to see if I'm on the right track. Okay. So plus r cubed sine of 2 theta times sine theta. Okay. And then the i's. So minus r cubed cosine 2 theta sine theta minus r sine theta plus r cubed plus sine 2 theta. Okay. So what we will have is, so this is our real component. Okay, so I'm kind of lazy about just simplifying this further, but u of r theta is equal to, oh my goodness, r cubed cosine 2 theta cosine theta plus r cosine theta plus r cubed sine 2 theta sine theta over r squared. And then v of r theta is equal to r cubed sine 2 theta sine theta minus r cubed cosine 2 theta sine theta minus r sine theta. Okay. Over r squared. Over r squared. Okay. Let's see. Okay. So if I made a mistake at some point, just let me know. But that is the simplified version of the polar function for u and v, right? So let me write out some comprehension problems for you to work with. So page 4, 7, 8. 10, 12. 18, 20. And that's it. Okay. If you have questions, let me know. Otherwise, thanks for watching. I'll see you in the next video.